will look like this. Notice the variable, right? Okay, A sub n will be a sequence, something like we've been studying so far already. C, any ideas?
Constant, no.
It is a number.
Probably center.
It's the center, yeah. So just like a Taylor polynomial will have this power series centered at some number, right? When you expand these out, see if this looks familiar. Look familiar? What's the only thing missing from it? Yeah, it's just a Taylor polynomial without a factorial underneath. Okay. And in fact, when we get to Taylor series, it will have a factorial underneath it, right? So not much different than you've ever seen. We're just putting it into a series. And what we're going to do is, where does this converge and diverge? Okay. So for what values of x? So we'll put a number in there. Does it converge or diverge? Just like a series we've been looking at. Okay. So the best way to look at this is through the geometric series. Oh, that's a G. Let's make sure that number's right. That looks just like what we've been studying, right? Something to the power of n. Right, so if we expand this out, x to the 0 is 1, right? And then x plus x squared plus x cubed. So this is a geometric series. Does this look like a Taylor polynomial that you've seen? I don't know if you've seen this one or not. This is just FYI, this is a Taylor polynomial for 1 over 1 minus x. Very close to e to the x. Okay. But that's what the Taylor polynomial is for 1 over 1 minus x, just for your information. Okay, when does a geometric series converge? So we would ask for what values of x does the series converge? So we already have a question we can answer. So if I plugged a number into x, which numbers would you pick and this would converge? I can't hear you, I'm sorry, I'm deaf. Sometimes in mind, not physically, I'm actually physically deaf. Yeah, right? So if x is between -1 and 1, we know that this converges, correct? Because you can plug any number between -1 and 1 in there. That's a geometric series, right? Good on that? Nothing you didn't know already, I hope. Okay. That?
Do you think you could go into explanation with that? Since we
Yeah,
went through
so
that?
basically what you're looking at is this is between -1 and 1, right? So if I plug 1/2 in for x, does this series converge? Remember, this is a geometric series with r equals 1/2, right? Does that converge?
You weren't here for geometry.
Okay.
Right.
Okay, you need to play some catch up. Yeah, so if you have a series that looks like this, and that number to the power of n is between -1 and 1, not including -1 and 1, then that will converge. Okay. So what we're doing here is just giving you a generalized series for geometric series and saying, when does this converge? So this right here is called an interval of convergence. Okay, there's one of your new terms for the day. So you would say the interval of convergence for that series is from -1 to 1. Okay. That's the interval of convergence. Okay.
It seems like a lot of the tests that we're working with, you don't actually have to manipulate the equation that much. I mean, sometimes you have to solve for a limit, and sometimes you have to like simplify it, but for the most part it seems like you're just looking for conditions.
Yeah, satisfy the conditions of the test, use the test to get a result.
What exactly is using the test though? Is that just like the simplification that sometimes you have to use?
So the integral test, right? The function has to be continuous and positive and decreasing, right? Those conditions are met. Then you can do the calculations with the integral test, and it will give you the answer. Does that make sense?
Yeah,
Okay.
but like, it seems like there's something like the comparison test that, yeah, you have to like simplify it and things like that, but you can pretty much just take your equation and compare it to, like, write it as being equal to another one and...
Less than or greater than, yeah. It is. Yeah, it's very mechanical once you get down to it, right? Kind of like we're looking at building a house and we had to have a septic system design, and it's like basically what they do is they dig a hole and they see how fast water drains out of it. It's called a percolation rate. They look at the soil, see what it's made out of. Boom, boom, those are your tests. Here's the result. Here's the size of your septic system. Done, right? It's very mechanical in that nature. Yeah, so. The other thing you'll want to know is the radius of convergence. They're related. So if you looked at that interval, could you guess what the radius might be? 1. Done so. Okay. Know the difference. Okay, because they'll be used interchangeably. And if you are asked for a radius of convergence and you give an interval, they won't count it as correct. Okay, they're very specific when they ask. It's, well, if your interval is from -1 to 1, it's like your diameter, so to speak, right? So what would the radius be? 1. Yeah. Yeah, so it's just basically what you're looking at is the absolute value of x is less than 1, right? That's your radius of convergence. Okay. So those are the two big things for vocab for today. Okay. So let's look at some series and determine where they converge. We'll look at what is the interval and what is the radius of convergence. Okay. And like I said, most of the time we use the ratio tests. So where does actually a couple ways you can do this one. Your book says use the ratio test. What's your first thought on which test to use? Yeah, exactly. That's the easier one here, right? This is a geometric series. If you rewrite it in such manner, right? So that term, in order for a geometric series to converge, has to be between, yeah, so in this case, if you're at this stage, right? And then multiply by 2. Yeah, so the radius is 2. Okay. So that's the radius of convergence. Okay. What you have to do with these is you have to check the endpoints. Okay, that's one thing that's a little bit funny with these. So if I have this series, so I have to check endpoints. Two is one of those endpoints, correct? So I'll plug 2 in here. And I'll analyze that seek series. So does that converge or diverge? Okay, diverges. Because what test did you use? What kind of series is this, Canyon? Yeah, yeah, it's a geometric with r equals 1, right? So that's one endpoint. Okay, what about this one? At least we could write it either way.
What are we using? Tests?
He's just checking that.
Okay.
Not just, he's not just like.
Diverges or converges? Okay, again, same test. Okay. So this one's a little more obvious. Because the geometric series, we probably didn't need to do this step. Okay. But if we were to use the ratio test, we had to check the endpoints. So I do want to show you the ratio test, just so you can see it. You remember the ratio test? Yeah. Put your n plus 1 up here. Your n down there. Again, you don't have to write this out like that if you're good with this. Fraction, you can write it like this as your initial step. I'm okay with that. So what's left between these two? Yeah, and these two, 2. Okay, so right there, correct? What does the ratio test say our limit has to be less than? Do you remember? What does that have to be less than for the ratio test to work?
Be less than
1, right? Okay, so you'll still get the same interval and radius, right?
And now you have to check it.
But the ratio test is inconclusive at positive and negative 1. So that's why we check the endpoints. Right? So check endpoints. Absolute value.
Yeah, but the ratio test is inclusive of positive, right?
No, at x equals positive or negative. I guess that would be more correct if I did that. This value right here, that makes sense now. Okay. Yeah. So whatever this value is right here, 1 and negative 1 are going to give you an inconclusive answer. So we have to check those, and that's what we did here already, right? In geometric series, we did not need to check the endpoints because geometric series has a rule on R equals 1, so we're good there. Good? Okay. Let's do one more. Like I said, they're gonna basically, this is basically gonna be a ratio test. So let's look at this series. A little bit nastier. So the question might be, does the series converge? Oh, sorry. Where? You'll always have the where question if you have a power series. So we have an alternating series here, right?
Mm-hmm.
The nice thing about the ratio test is it gets rid of that negative, so you don't have to worry about it. Okay, so if we're going to use the ratio test, right? And if you're concerned about it, you see how big these problems can get, right? So n plus 1 over n. These we can get rid of because they're negatives or positives, it doesn't matter. Okay, the absolute value takes those out. So what's left over? X minus 5 to the first. The ends cancel. Then we got 4 and n, and n plus 1 can't do anything about that. Right? Okay, what's that left over? What happens to these two as n approaches infinity? 1, right? If you use the highest exponent rule, n over n is 1. So what we're left with is x minus 5 over 4, right? So it has to be less than 1. Right? So this is where the ratio test kicks in, the results. So the absolute value of x minus 5 has to be less than 4. What's your radius of convergence? 4. Okay. Yeah. The interval we can't really say yet. Okay.
So do you not add the 5 over?
That's what we're going to do now. We know that the radius is 4 because of that number. But if we add the 5 now to both sides, we get 1 to 9, right?
Did you get the 4 from the denominator?
Yeah. So multiply 4.
Right.
So from 1 and 9 are endpoints, right? We need to check those endpoints. So go back to your original. Plug 1 in, right? So we get negative 4 to the end. What happens with that? Does it converge or diverge? Okay, if I combine, can I combine these two? What do I get? Right, negative 4 times negative 1 is 4. Right? These cancel out, right? What series is that? And it diverges, right? Because it's a harmonic series. You can just say that. It's very nice. Okay. And then how about 9? It's 4 to the end. Okay, so we have these two can cancel out right away, right? So we have this series. Negative 1 to the n over n. It looks very similar, right, to the harmonic series? what does it have in it? It's alternating. So does this meet the conditions of the alternating series test? Decreasing and positive. The absolute value of the terms are positive, right? 1 over n is positive and decreasing. And this is alternating, right? That series converges. Right, so again, the questions we answered was 1 over n decreasing and positive. Yes. And it's alternating. Converges by the alternating series tests. Okay. So those, if you see an alternating series, that's your first thought should be to test it with that. Okay. Good. So lots going on in these questions, right? But again, most of the time you just use the ratio test, get your radius. What's our interval of convergence? Did 9 work? Yes, right? But 1 did not. So all we do is put the less than or equal to on the 9. There's our interval of convergence. Okay. Good questions? I'm going to show you some more tomorrow, specific examples. So you got it. This is actually not going to be due till Friday because I won't even be here. So on Thursday. That's 55. This is 20. So that's just the scribbles.
That's 49.
Yep. 49. All right, due Friday.
Hey, is that a 45 or 50?
45. Again, if you give some of these a shot, bring me questions the next, tomorrow. We can answer those.
Are you gonna be at home somewhere?
Just after school. I have to be in Cold by 5:30, so I have to leave by 4:30. Keep studying those memory cards. We'll do ratio and root test cards. Hopefully we have time right now. Nope. Remind me tomorrow.